All right, welcome back to the Barbarek channel. Here we are again, and we are covering our MIDI pedal. Last time we covered where we left off was here. Let me just bring this up. Here we had covered, in the first installment, we covered how to connect our two pedals, RC500 that uses TRS cable and Digitech Whammy that uses more traditional DIN5 cable. We cover all of that, how to send the commands, and in the second one we kind of made the pedal with a switch and LED option, so it's kind of a more looking like a pedal. And please check that out if you haven't seen this. Just to note, there's details and links. There's links and details of this video in the description, and all examples are there, so you don't need to take notes. That's normally how this works. So what we have here for today, what I prepared is adding expression pedal support to our MIDI pedal. I have Audio EXP, super cheap pedal, I think, something like this. It has here adjustment pot, and it's super cheap. But the point is, it will work, and we just want to have something to work with. There are some nuances. The pedals, this has a pot that controls minimal resistance value, and there is also a polarity switch, but some other pedals could have, for example, a capacitor there for better noise performance, I'm guessing. But I would not presume anything without checking documentation or looking up somewhere to get a schematic of the pedal. So companies sometimes release expression pedals that is specifically targeted to their equipment as well, and all this goes to say, just be a bit careful with what you're using and what you have, with your equipment. We'll focus on using the part that covers just the expression pedals are normally implemented as passive, just potentiometer inside, nothing else. So we'll focus on that part first, and we're gonna then delve into other stuff. So here, this is my expression pedal. I went through. I initially dismantled my pedal and then checked where all the wires go. I put the pedal, this diagram, verified everything, but you don't need to do this. And I actually don't even advise you. I would advise you against that, because you probably lose warranty on that. Yeah, you lose warranty on that. So but you can just measure resistance between tip, ring, and sleeve, and you can figure out how this works. Here, I'm just going to quickly go through this. As you can see here, there is this, it's a pot inside. There's nothing in it, and there is, like pedal, when you rock the pedal, there is a little kind of a attachment that just rotates the shaft, and that's it. Here there is 1K resistor on the Viper that, if you wire it incorrectly, it prevents, it's kind of a current limiting thing. You can adjust here. So the pot is 10K. Some other pedals have higher potentiometer values. There is adjustment here. There's 50K pot that sets the minimum value. Polarity switch just changes between, there's two settings, M audio and other. when M audio is configured, ring is attached to this end of the pot, and the main thing is where your tip is, and your tip is where your Viper is connected. It's connected to the tip. In other position, the Viper is connected to ring, and the tip is connected to this pin 3 of the pot. This is a bit important because sleeve is also connected to chassis. It's not chassis, but it's connected. There is a metal plate at the bottom of the pedal, and this is kind of probably to help with noise, but I don't know how effective that is really. So in essence, it's just a pot. So let's code around that pot first. So let's see what is the minimum thing we can work with. So here I have I'm going to use a pot, just a pot. I'm going to wire it up in such a way that Viper goes to this GPIO 28, which is also, there's analog digital converter there. And Raspberry Pi has 4 such pins. One of them is currently used for some temperature sensor on a Pico board, so you can use, but RP2040 has 4. Moot point, we can use only 3. And I'll connect one side to 3.3 volt source. The sleeve is going to go to the ground, and it is probably a good idea to have it to the ground because of that chassis connection. And yeah, that's about it. So let's bring up Tony. Oh, I think I killed it. So let me start it. And what we're going to do is, again, there's no shame in going and using the simplest possible examples from getting started with Raspberry Pi Pico. It's simple stuff. If we can't make simple stuff work, we can't make more complex stuff work. Stands to reason. So here's the most simple and probably most quoted kind of a example out there. We won't be using that. We're going to go a bit more. If you remember last time, we used the MicroPython async IO, MicroPython async library, and here it is. Like if you remember from last time, this is what we use. There's how to use push button, how to use tasks, how to use other primitives. I covered that. Have a look at that. But here we can see that if we compare these two, they're not much different. I know there's a few more lines, but there's not much into it. So what I prepared a program that I'm going to run. Where's my Tony? So let me go through this real quick. Oh, okay, let's stop this. So what I forgot to wire up the pot. And as you can see, because ADAC pin is now floating, there's lots of noise on it. So that's what it will say. Ground, I have conveniently put the ground here. Well, actually, what did I do on that diagram? Did I put... oh, yeah, ground. So we're going to go to ground. So our pin 1 goes to ground. Oh, I can't reach that, can I? Yeah, I'm just going to take white. To the ground, just because it's a bit longer lead. Black goes to 3.3 volts. And you really shouldn't be doing this like this. This one is powered, the board is powered at the moment, and I'm messing around with wires, and if I touch anything here, who knows what might happen. So just be careful about it. I think it's here, isn't it? It's like, what is 3.3? Then, yeah, okay, that should be it. So let me run the thing. Let's bring up Tony again. Reset. Let's do this. And we still get this reading, okay? Let me explain the code a bit here, real quick. So we are using async IO as before with those primitives. In primitives on in the documentation, you can look it up. This is async ADC, analog to digital converter. How this is constructed, if you look at the Python, that getting started thing, it's here. This is ADC. This is how you define that you want to read analog values from that pin. That's it here. That's it here. So we just wrap it up into this analog implementation. We set up the main loop, and it just awaits. So it's a slightly different way of using ADC. The code awaits, the library awaits to give back value, but I define here that if the value changes in 512, whatever. This is just when you read from ADC, you read it's assigned 16-bit value, so it's from 0 to 65,535. I have it written down, so I'm just reading that number. But it is 16-bit value. Our analog to digital converter on Raspberry Pi is 12-bit, and that's effectively 0 to 4095. So 4096 values. So our value isn't really, when we read it from ADC, it's, you see here, you see 53,000 or whatever. If I turn around this pot, you can see if I go down, the value goes down, right? And you can see that there. And you know, it's noisy. But in reality, this should be divided by 16 to get a value, the actual reading. Having said that, and this is where it's useful to know how to read data sheets. The actual effective number, if I can find that somewhere, you know, you have RP2040 datasheet microcontroller. You can find somewhere, I think it's effective, oh, what's the name of that? Effective number of bits. Did you find? It is one. Okay, here. It says effective number of bits is 8.7. There's some, and you can see here, input impedance of ADC is 100 kilo ohms, and there's more to this. And then, you know, you can even look into Raspberry Pi Pico datasheet, because it's not just the pin, it's the implementation of the board as well, how it works. So internally, it's not super precise, or you can make it ideally precise. ADC, so there is some noise, there is some, so you can't really get 12-bit resolution. This is effectively how much you get. We say 9, let's call it 9. So we are really using 512 values effectively. In the end, it's a moot point because for our control change command, we are going to only use 128 values because that's what's supported by MIDI. So, you know, not really a huge difference. There's also a note, and this is where I said, if you look it up, Raspberry Pi, let me try to find that. There is a pinout somewhere, I think, that I have it. Okay, I'll just find it real quick. Raspberry Pi Pico pinout. There it is. There's also this analog ground pin. There's only one ground pin on RP2040, and this is where, you know, again, reading datasheets, and I'm not great at it. I'm not really a huge, you know, like, it's a skill reading datasheet. I just know enough to be dangerous, I suppose. But there is analog ground, and there's only one ground pin on this chip. So this is a property of the board, not of the chip itself. So if where was that? A ground is the ground reference for these pins. And there is a separate analog ground plane running under the signals, and the performance of ADC is not critical, and or ADC is not used. You don't really need to use it, but like, idea is that it is less. It's decoupled from. At least it tries to be less noisy than digital pins, because the Raspberry Pi, this RP2040 runs very fast clock. So maybe if we connect to different pin, if we connect to this analog ground, that maybe it's going to give us better performance. That may be the case, may not be the case. We are still connected to 3.3 volt supply, which, you know, here it may also be noisy. There is ADC VREF here that you can make this reference better, less noisy, more precise. It's all in datasheet, implementation, guys, whatever, like, there's loads to it. But sometimes, you know, for our pedal, I don't think for now we're going to care about that. In the end, we'll have to be probably more smarter how we read this information from our ADC to take into account some of these nuances, but we'll come to that. So let's see. I have it here. I'm just going to rewire this to analog ground. I think that's here. Okay. And maybe it's a bit less noisy. And, you know, it's very hard to tell if it is. All right. So how do we translate this? I'm just going to reset this. How do we translate this into a pedal? You know, if you have a particular expression pedal in mind, then it's simple. You know, you know the diagram, or you figure it out somehow. But if you want to support not just one, multiple ones, you know, that's a different matter. But for now, it's simple. We just need to figure out how output is wired up, and then we do something like this. So we create our own wiring. So when M audio option is set, our ring should be 3.3 volts. this we are connecting this pin number 3. That is, this is the switch option, so it's ring, and our wiper should go to, this is our option, to tip. So wiper goes to tip. Okay, so wiper goes to tip, wiper goes to ADC, ring goes to 3.3 volts, and slave is always going to go to analog ground because, you know, that's how it's because of that chassis that I mentioned. So I prepared here my plug. I'm just going to remove pot. Now it will probably come as no surprise that we are actually going to do the same wiring as the pot. The pot was there just for demo. So where's my tip? This is my tip. It's red. That goes to, yeah, yellow. Not great choice of colors. I'm gonna mess it up, right? Okay, let me just rewire this. We said tip, right? Tip goes to it. So let's keep it so we know that this is yellow is. Yeah. And then ring goes to 3.3. These crocodiles are great. So where is that? So there was black one, yeah, 3.3. And sleeve goes to analog ground. There it is. I plugged in the pedal. Let me zoom out a bit. Maybe it's going to be, make some room here. Connected to M audio. Okay. It's getting busy here. All right. I have it wired up, I think. Let's give it a try. We're going to use exactly the same code as for the pot. I just made a slight change, and I'm just going to go and show that on Tony. And as before, I'm going to paste it here so we can discuss that. So I just divided by 512. And these are not really connected. These I just arbitrarily selected this value here just to trigger reading the value from the ADC. We will in future, we will have to change this and figure out what do we do when value goes up, when value goes down, just to make it a bit less noisy, because this will affect our pedal and how our pedal works. But this is, as you can see, I just divided by 512 here, the value, so we get our command change value there, right? So I'm going to add this, and hopefully we get something to play with, you know? Is this working? Let's see. Okay. Oh, yeah, it does work. Okay. So, as you can see here, I hope you can see I'm rocking the pedal. 127, that's maximum. And I slowly move down. And I get to 0. That's cool. It's working. And then if I roll this one, look at that. You know, it increases, and I can set the minimum value. So say I want my minimum value to be 100, and you would expect that it goes to 127, right? And you see how slowly it moves? That's because just the whole rotation of the pot is needed to make up from 100 to 127. So this is just, you know, like we covered this, obviously. You know, I can do this, and yay! So there you have it. From how I see this looks like a linear pot that is there, and that's why I set that in the diagram there. So let's use Whammy to demonstrate this, right? I don't know how I'm gonna fit this here all into the So I'm just going to move this, all of this, to the side, and you'll just have to trust me that I don't have any magic in the background. Okay, so let me bring Whammy. I'm just gonna wire it up. Okay, I have everything wired up there. I hope I'll try my best to do this. You know, it's a bit tricky holding the guitar, and there's an absolute mess on the table. But let's go through this. You know, the code I'm going to use is exactly the same as what we used in the previous one. I'm just going to change a few things here, and let me go real quick through this. You know, like we have, I just changed some of the commands. So I have Whammy, I'm going to turn on and off by pressing the button. And this is one is, I'm just going to kill the previous program. So I'll have 2 octaves up, on and off. I think that's what this is. I have toe up and down here, but this is really this control change 11 and value we're gonna pass in. So in the previous version, we had only control change 1, and we were trying, you know, like switching on and off. So here, when we toggle the switch, we are going to send this command 1 and command 22, this program change command that will change our options on Whammy. Does that work? That should work. That code. Oh, actually, I didn't send it to my board yet. So let's go through this real quick. The rest of it, you know. So this did not change from the last time. What changes here? The part that changed was how do we deal with now expression pedal. So here, if you remember the previous, just the previous example was exactly the same. I just put this into a separate function. Here I still await this value. Ignore this for a bit. Here I'm just going to move this here. So then I determine value for that control change, and it is divided by 512. We just saw that earlier. Now I prepare my command that I'm going to send over MIDI. This is, I call it C partial. So this is the command change 11, and I just append this value to that. And I'm going to print this out, this command and the value, just so you see what's being sent on MIDI. And I'm just going to add this outline, just so it doesn't print out. This returns number of bytes written to the UART. I just don't want this to be clogging my data. So, and here I have everything the same as on previous video. Pin 14 is going to be used as my button. Red LED is going to be, you know, toggling. In addition to my Digitech Whammy toggling the LED. And then I set up this MIDI UART, and we saw how ADC is connected, you know, how it's used. Set up push button. When button is pressed, we toggle. And here I create a task, and task is just going to do, what it's going to do is just going to run this in background. So whenever we yield control, and we yield it here, our button can be polled, etc., etc. There are nuances with async operations, but this is, we're going to call this method. We're going to pass in our ADC and MIDI, so MIDI can be, you know, written to. Anyway, can I just send this? How do I do this? Run current script. Will this work? All right, nothing happened. Do I need to? All right, I don't know. Does this work? There's only one way to find out, right? So, all right. So as you can see here, I just move this configuration here. And when I press it, it will make a change here. So does it work? Okay. Yeah, it's working, right? So the thing is, as you can see, when I press this pedal and I rock it, it kind of conflicts with what I'm doing here. So if I do this, look at this. Because this one quickly makes it 0, the value, and this one. All right, so let's just focus on this pedal here. So we have 2036. Right, it's working. Wow. Did you expect anything less? No? So now that we have all of this, okay, so you wonder, why is this any good? Why don't we just use this pedal? And, you know, besides obvious things like, let me just turn this off for a bit. Besides obvious things that we can control various different, you know, options, or coordinate sending the commands in between different pedals, there's also one thing. We can actually program this pot to work differently. So for example, let me just show you this. So I'm going to use this here. Let me just stop everything. Everything is exactly the same. Nothing changed, right? So nothing changed. What I added here, and I'm going to go through this real quick. This is exactly the same as the previous one. Let's get this out of the way. I added this translate pot value. So once you get a reading from the ADC, this value, you can do whatever you want with it. You can translate it. So what I decided was, I'm going to use this piecewise kind of a, this is very simple code, only 10 lines or so. But what this translates this to piecewise linear approximation of whatever function you want to put. And I put here audio pot piecewise approximation. What that is like pots are not organized. And I have a video somewhere or a post somewhere how, for example, Alps in their documentation, it's not a proper audio curve. It's like there's a linear portion, linear portion, linear portion, and linear portion like this. So what we're trying to translate here, this is, you see here is what I read the datasheet, figured out that 95% of the pot rotation gives you 99% value of the resistance, 72% gives you 40% of resistance, so that is a steep part, and then this part is like slowly increasing. I just multiplied this with our 65535 just so we don't need to on the fly calculate these values, and makes the code cleaner. And what I do is here I figure detect which part of this piecewise function it is, and then I translate that into a value. It's relatively easy. Well, when I say relatively easy, it took me 2 days to figure out this. Once I multiplied everything with here, it made things way easier. But this essentially, as you've seen, it's a linear pot. I'm gonna make it audio pot. So first, I'm just gonna to show you, you see how slowly it moves, and then all of a sudden, just goes very quickly to 127, you know. But and here it's very slow, very slow. It's nearly half of it. Half of it, let's see if I get half of it, is 20, 30. And the rest of it is 100 extra for the value that goes. So half of it is very slow, then the rest of it is fast. Let's see how that sounds actually. And I hope you notice that it is a different sound. So if I wanted to make this linear, there's no bother, you know. I can make this, I just delete this, and it's one linear function. So I can just stop, send this again there. And if you can see that it very quick goes through all of them. So it's a different sound, you know. I hope that makes sense, but like it's very powerful. You can do all sorts of things, you know. You can create whatever, you can approximate whichever function you want and put it here. I think it's quite funny because you can do all sorts of things with this. So I have this here. Let me switch this to other, and let's see what we get. Okay, what we get a bit peculiar functionality. You know, it doesn't go all the way to 0, and it doesn't go quite to 128, and this doesn't really work because, I don't know, it is a bit weird. It goes, you know, to 125, whereas it was going a bit less, and then you have no real here. So what I'm going to do is see how can we, why is this so? And let me move Whammy away and let's focus on what's going on. Okay, I rearranged this tiny bit so we can see better what's going on. But essentially what's happening is that once it's wired in this other position, we don't have the same connections. So we have, you know, ring is, you know, physically connected to 3.3 volts in our case. So it's kind of you can change that. So when the switch turns, our ring now goes through, so 3.3 volts go through current limiting resistor. And I suppose this is why it's here. And through this part here. And what we're really seeing is a sort of a, doesn't really, our ADC doesn't really get correct voltage, you know. So it's a bit weird, right? And again, the problem is we can't just rewire pedal. So if we want to support multiple different options, we can't just rewire pedal because this is, it's hardware, it's hardwired. So the only hope we have is to actually fix this somehow to be more flexible. So if, for example, we had an option to configure this way, or rather this should go to analog ground, but so this way, depending on the switch, we could, for example, in this configuration, we can drive this pin to 3.3 volts and then we measure this is now ADC that we are using. But if we switch switch the other position, then this will actually be Viper, and then we will use this one as ADC, and this will be 3.3 volts. So in order to support this, this is our now final kind of a diagram. Is I'm just going to rewire our interface slightly bit, so our sleeve is going to stay to analog ground. That does not change. But now ring is, I think this is ring. Yeah, so ring goes instead here, and tip goes here, right? And you may have seen that something happened, and what happened is I probably shorted something and reset the thing. I should be probably disconnecting this, or I might get it burned. I should be, because I'm rewiring live board, so sooner or later I'm gonna mess it up, and there'll be magic smoke leaving Pico. So if I look at this, like I'm just gonna change this real quick. So here, if you remember last time, this is the last example. So my ADC is, what are we? Let me just go back to M audio. Okay. So ADC is now, it's getting a bit nuts. Let's go back there. So ADC, our Viper should go to tip, right? So tip is ADC 26. So 26 should be our ADC. So we put this 26 here, right? But now I just put this driver is going to be here. So I just put like, I call it driver. Just drives high and gives us some voltage. Now, one word of caution is though about this is that you should always look into datasheet and see what are the limits you can push this. How much current do you can drive here? Can you drive current for a prolonged period of time? And so as you can see, I just changed this here. I changed which pin this is connected to, and that's all it took. So let's see. Well, actually, I forgot I can press this. Okay, so let's see what happens. Oh, what am I doing? 26, 27, right? I'm not getting any power there, right? Silly me. So it's actually going to be 27 here. I kind of incorrectly. So let's go back to that diagram. 26, 27. Where I was looking. So what did we say? Our tip is 26. Is that what we need? I keep forgetting this, right? Let's go. I'm not embarrassed for forgetting these things. It's tip, yeah. Tip 26. Let's get this right? Stop, run. I probably messed up again. It's other. I'm sure. What did I do? Oh, you fool. Okay. Yeah. That was a bit of a, that wasn't great. Sorry about that. So I always mess this up because I put my hand here and I just accidentally turn it around, but I forgot I left it there. So now we have an issue here, slight issue with that we spoke about. So here's the deal. I don't need to change anything. I just need to reconfigure my pins, and you can do this in software. So this is one of the ways that you're more we made it more flexible. So now if I go do this, it goes from 0 to 1 to 7, and then okay, and then you can even use this. So it retains full functionality. Now, if I'm not mistaken, I'm getting, when I go down, it increases. When I go down, when I go up, it decreases. So, you can code is relatively easy to configure. There are other options, if I want to go and follow that path, I might use some kind of a multiplexer or something like that, analog switch or something like that. But I don't think at this stage there is a real value in doing that, because this is the simplest possible thing. It's working. We should be okay with that. So let me just look into. So let's finish up here. Right, we covered a lot, and I think I thought this would be shorter, to be honest. So what we covered was how the expression pedal works. Okay, so let me see that. Let's go through that. And this is, some of them don't have this switch, but most of them have this part similar. It's common, So how it's wired, it's up to the manufacturer. We are flexible with that. Volume pedals work similar way, but they might have different pot taper, especially some of the Boss's pedals. So again, you could transform input resistance to however you want to do it. We cover how to handle handle pedal with using analog to digital conversion provided by Pico, and we at the same time we used async IO, which was, I think, very good. We also covered how to manipulate this pedal response, as I said. That's one of the possible ways. With this, you can achieve whatever you want, really, and you can do crazy stuff like you can, sky is the limit, really. When you click on a button, you can even make this expression here. You can make this do a wavy sound. It doesn't need to be reading your pedal position. You can do whatever you want. You can program it to just go around and then make some noise with your Digitech Whammy. Again, depends on the pedal you're controlling. You're only limited by that, but everything else is just great. And finally, we covered how to support that polarity switch in the end. I think we covered a lot. Hopefully this was useful. Stay tuned for the next part, and hopefully that will be as fun as it has been so far. But we'll cover some external pedal switches, and stuff like that. So make sure you stay tuned, and until next time.